Hey everyone, this is Rajan Chadrao coming at you again live from the cockpit of a Ferrari F1 car. I believe this is a 2020, 2019 car. I'm not entirely sure, but sitting in the cockpit as I do. But today we're going to be talking about doing FEA analysis on control arms. This video is going to cover the setup of these control arms, so covering the boundary conditions and also the mesh conditions. Before I go into this video, a big precondition is please be aware of the limitations of your system. If you have a laptop or a computer that isn't very computationally powerful, then I highly recommend going towards settings that are easier to solve. You may get less accurate results, but it will solve much quicker. I do highly recommend using the PLM Center if you are at Clemson, or if you're at another university, using whatever computers your lab has available that are more powerful than your laptop to run these simulations a good bit faster. But overall, the goal of this video is to gain a conceptual understanding behind the boundary conditions of how to model control arms in finite element analysis using ANSYS Workbench and ANSYS Static Structural. I'm currently using the 2022 version of ANSYS Workbench. If you have a different version, I really hope a lot of this information carries over. If not, well, I mean, good luck. I hope I hope a lot of the settings are similar to what you're seeing in your new version, but yeah, this is meant for the 2022 R1 version of ANSYS Workbench. It hopefully shouldn't change much. What I'm going to do is start off by showing everyone a completed version of what a good ANSYS Workbench setup for control arm FEA looks like. We're going to start off with our engineering data in one section, which is our material properties, where our material being used is selected. We can customizably select our elastic modulus, ultimate tensile strength, and just about everything that deals with material properties in this sect. From there, we want to load in our geometries. For each of our control arms, we have a separate geometry file. This is going to be an assembly FEA instead of simple component FEA, and this is to improve the resolution and improve the fidelity of our model and get more accurate load analysis. From there, we have individual static structural nodes for each of our four control arms. That is rear upper, which is RUCA, rear lower, which is RULCA, front upper, which is FUCA, and front lower, which is FULCA. So now that we've seen what an ideal setup and a completed setup of control arm FEA looks like, we're going to start off with a blank workbench screen and get started from there. And before we start off with the FEA analysis, we need to look a little bit closely at how to make a good SolidWorks model or a CAD model of what we want to model or what we want to represent in this FEA analysis. But before we do that, using our feedback from last video, we're going to start a tiny bit of lo-fi music. Now that we've got this started, we're going to start off again with our CAD model. I used SolidWorks to model my control arms, but feel free to use whatever CAD modeling software you prefer. If you are on the Clemson FSAE team, we do recommend SolidWorks since that's what we teach in our classes. So using SolidWorks, I chose to model the control arm, a dummy bearing, which is a stand-in for the spherical bearing that gets pressed into the bearing cups of the control arm, and a snap ring. Using all of these individual components helps us accurately represent exactly the stresses that this control arm is going to see, following the load path between the dummy bearing, the snap rings, and the bearing cup of the control arm. Accurately modeling this helps us prevent unreasonable deformations that may occur from the absence of a bearing. For example, I used to run simple component FEA before I started doing this assembly FEA, and that's when I started to notice the bearing cups compressing and becoming more elliptical instead of cylindrical. And that's because the load applied would deform it in such a way that the circular shape of the bearing cup would not be preserved. So using all of these individual components helps us preserve the shape and accurately or more accurately represent each of the stresses that each of the components is going to see versus doing individual component FEA. So let's move on to our ANSYS Workbench setup, and for this video, we're going to use the front upper control arm as an example. During this example, which is built during the 2024 design season, which is for the 23-24 season, the front push rods are mounted off of the front lower control arms. So we're using the front upper control arms as an example for what a control arm looks like without a push rod load. This is a simple loading of a control arm, again, without a push rod load or even without a toe link load. If you want to add those can be pretty simply added, as I'll refer to later in the video. But let's get started. I'm going to share my screen now. I've got ANSYS pulled up. Here we can see a blank ANSYS workbench setup. The first thing to pull in is engineering data. We want to make sure that all of our materials accurately represent the actual metals and alloys that we use in real life. For us, that is steel 4130. And you can load in steel 4130's properties by right-clicking engineering data and hitting edit. So right here we can see structural steel, and down here we can see each of the individual properties, including density, tensile yield strength, compressive yield strength, tensile ultimate strength, and a lot of other things. Almost all of these can be pulled from matweb.com, so feel free to use that resource, but we want to make sure that, again, the material that we're testing with accurately represents the material that we're going to be using in real life. After we've loaded in our engineering data, the next thing we want to do is load in a geometry. In the example we covered at the start of this video, we had a geometry for each of the individual control arm files, which is what I highly recommend. If you can have all of your control arms in one workbench file, that would be absolutely incredible because you can do everything in one environment. For this example, we're using one single control arm, which is the front upper control arm, which is why we're only pulling in one geometry, and then from there only doing one static structural analysis. So once you pull in a geometry node, what we can do is hit a right click on the geometry node, do import geometry, hit browse, and then we're going to go in and select the appropriate file path for our front upper control arm geometry. Again, this does depend on which control arm you're doing an analysis of, but for us, we're doing the front upper control arm. And as soon as we load in that geometry, we're going to do a quick CAD analysis of exactly what we're representing in that geometry. So by switching over to my other screen, what I'm going to do is show all of you exactly what we're representing in the CAD model. So here we have a FEA control arm. This is separate from the actual control arm that we used this past year because the actual control arm has each individual tube for the control arm as an individual body. The FEA assembly has the entire control arm as one body, which helps us insert the dummy bearing, which represents the outer diameter and the height of the spherical bearing that we're using for this year, as well as the dummy snap ring, which represents the outer diameter, inner diameter, and height of the snap ring that we're using for this year at all nodes. Again, quick reminder that the A node for these is the one that is forward to the car, towards the front of the car. The B node is the one that is rearward to the car on the inboard, again, towards the back of the car. And the C node is that which is outboard to the car, facing out, away from the car. Now, once we make our assembly, which has the dummy bearing, dummy snap ring, and the control arm all included, we're ready to load that into our ANSYS workbench assembly. Now, as I said before, this assembly can be loaded in by right-clicking our geometry node, hitting import geometry. Now I'm going to do replace geometry real quick just to show you real quick, but we want to choose FUCA FEA Assemb, which is our assembly, which has the dummy bearings and snap rings all inside of it. Now we have our engineering data and our geometry all loaded in. What we want to do now is conduct a static structural analysis. So we're going to come over here to our tree on the left, select static structural, click and drag, bring that over to the right. And once that loads in, we're going to have a static structural analysis node in our ANSYS workbench. And there it is. Once we have that, we want to make sure that this analysis refers to the element properties or the material properties that we have selected before, as well as our geometry that we selected before. The one really great thing about ANSYS Workbench is that we can click and drag each of these individual elements to actually represent the element properties and material geometry that we specified earlier. So looking over here at engineering data, we can click and drag right where this bottom right triangle is and drag it over to the engineering data. As you can see, that draws a line to display that connection, and we can do the exact same thing with geometry. Once both of those have loaded in, you'll see a green sort of two arrows pointing in a circle, and that means refresh. And we'll double click on that to open ANSYS Mechanical, and from there we'll be able to look at our actual ANSYS model. And now I'm going to pause the recording. Now, once your model has been loaded up, we're going to continue to our ANSYS Mechanical window, which has just opened up. So I'm going to share my screen again and show y'all what that looks like. We're seeing representation of what our SolidWorks model might look like. This includes the dummy bearings and the snap rings and our control arm. So we can see all of those by choosing our body selection up here at the top of our ANSYS Mechanical area. We can see that our entire control arm has been selected. Our dummy bearings are here, as well as our individual dummy snap rings. For each of our selections, you can see when you've actually selected them by seeing when it turns green. Now, the number one thing that we want to do as soon as everything has been loaded in to our ANSYS Mechanical area is double check our contacts between each of the surfaces. So we're expecting our dummy bearings to be a press fit between the dummy bearing and the bearing cup, which is this area right here. Let me change that face selection, but this area right here of the control arm to the actual bearing cup. Again, like I said, we want to make sure that these are selected properly and accurately represent the contact that physically occurs in the real world between these two objects. Now, for each of the contacts that we represent at each of the nodes, there are three contacts. There is a contact between the dummy bearing and the bearing cup. There is a contact between the dummy bearing and the snap ring. And there is a contact between the snap ring and the bearing cup. And we're going to take our turns and organize each of these into folders. So we're going to see each of those by navigating to our left tree over here, again on the left side of our screen. And we're going to take a look at connections and hit the drop down. We're going to see a subfolder called contacts pop up. We're going to hit the drop down on that. And then we'll see one of 9 contact regions. Now, ANSYS auto-populates each of these contact regions based on which components are actually touching each other, and this is decently accurate for our uses. We're going to see 9 contact regions because there are 3 contacts per node, and there are 3 nodes. Again, 3 times 3 equals 9, so we're going to see 9 total contact regions. But we do have to make sure to go into each one of these and ensure that each of the contact parameters are correct. For each of these contacts, our ANSYS auto-populates to a bonded contact. Now, a bonded contact represents one that is welded together or epoxied together or something that is physically attached together. Again, like the name implies, bonded. What we want to enact on this model is something called a rough contact. Something which is not bonded together. There's no physical attachment between the two components, but instead there is more of a touch, a barrier contact between each of the surfaces. When I press fit a bearing into a bearing cup, there is going to be a rough contact between my spherical bearing and my bearing cup. So what we're going to do now is go through each of these individual contacts and ensure that they are rough contacts and ensure that they follow the correct parameters. So we'll start with contact region 1 right here. When we click on a contact region, we'll see 2 views auto-populate over on the right side of our screen. Now you can click your middle scroll bar and the control key to navigate this, similar to how you would navigate SolidWorks, to ensure that your surfaces are correct. Over here, we see the B node as seen on our main screen. We see the dummy bearing of the B node, the top face, interfacing with the bottom face of the dummy snap ring of the B node. Now, this is absolutely correct because these are the only two faces that actually touch each other. So what we're going to do is change from bonded contact as seen down here at our bottom left. Let me know in the comments below if my mouse or my cursor is easy to see. That'll help me in future videos if I can actually use my cursor as a guiding pointer for each of these. But as you can see down here, our bonded contact, we want to change that to a rough contact. And since our face selection is correct, again, we want to double check that. Our target and our contact is correct. We're going to click here and add that to a group or a folder, and we're going to call this our B node because that is part of the B node. Now for our contact region number 2, we're going to see the dummy bearings outside face and bottom face over here interacting with something which should be pre-selected. Okay, there it is. Sometimes you have to reorient the control arm to actually be able to see which faces it's interacting with. Now, for the bearing cup, or for the dummy bearing to the bearing cup interface, we see that on the dummy bearing side, we have the outside perimeter of the dummy bearing and the bottom face of the dummy bearing touching the bearing cup, which on the contact side is absolutely correct. There are no other components of the dummy bearing that are interfacing with our actual control arm bearing cup. So now let's look at our target body view, which is our bearing cup. Over here, we can see that the actual face where the bearing interfaces with the bearing cup is selected and the bottom face is selected, but we also have the inside of the snap ring groove selected. Now this is incorrect because the inside of the snap ring groove in no way interfaces directly with our bearing cup. So what we're going to do is hold our control key and select both of the surfaces that actually interface with our bearing cup or our dummy bearing. And once both of those are selected, since this is our target body view, as shown by the selection on the right side, we're going to hit target and hit apply. And that's going to change our target selection to only those two views, which is where that dummy bearing interfaces, like I said earlier. Once again, let's not forget to change the bonded contact to a rough contact. And since, as we can see, this is our B node, we're going to click and drag this feature down to our B node. And now let's take a look at contact region 3. This represents our C node. We've covered the dummy bearing to snap ring interactions, so let's go ahead and try to find our third contact for the B node. And then from there, you'll be able to replicate all of that for each of the other nodes. So now we can see here that this represents the contact between our dummy snap ring and our control arm, or our bearing cup. So we can see that on the dummy snap ring, we have the top face, the outside face, and the bottom face selected, but not the inside face, because the inside face doesn't actually touch the control arm. But if we make our way over here to the target view, we can see that on the control arm, every single face on the inside of the bearing cup is selected. This is wrong. The snap ring doesn't actually touch every single one of these faces. So what we're going to do now is go in and hand select each of the inner snap ring faces, or the snap ring groove faces. So we've got our inside face, we've got our bottom face, and then we should be able to zoom out, look from the bottom, and get our top face of the snap ring groove. Now, as we look at our snap ring groove, each of 3 faces that the snap ring will possibly touch are selected. So, as we can see over here, this is part of our target body view. We're going to go over to target, left click on that, hit apply. And so now our contact body and our target body accurately represents which surfaces will be facing each other. Once again, do not forget to change this bonded contact to a rough contact. And once we're done with that, we'll change that to our B node. I'm going to stop or pause the recording now. Please feel free to pause this video we've just completed all of our contacts for the B node, and that is the dummy bearing to the control arm, the snap ring to the control arm, and the dummy bearing to the control arm. Once you get these three contacts sorted for each nodes, that is the A, B, and C nodes, feel free to resume this video and we'll get started from there. Gonna pause the recording. All right, everyone, hopefully at this point you've finished completing your connections between each of your bodies. So as you can see here, I just got done completing my A node, my C node, and my B node, or A, B, and C, depending on whether or not you want to follow alphabetic order. And now that we've got all of our contacts sorted, it's time to set up our supports and our loads. So we're going to start off with supports, but before we get into that scope, it's very, very important to understand how the control arm fits inside an assembly. So we're going to take a quick pause from our ANSYS model and take a look at some CAD models to see how the control arm fits inside the assembly. Now, before we look at the CAD model, I wanted to go over three things really quick. We're going to be using a lot of cylindrical supports in this FEA model. Now, a cylindrical support has 3 degrees of freedom, one of them being axial, one being radial, and the final one being tangential. Now, pretending that this is the axis along which our column support is enacted. Suppose this is the up and down direction for our bearing support. If I have a column support along this axis, a radial support is one that represents radial deformation along any possible radius of this part. Now, if radial deformation is free, that means that the radial aspect of the part is free to move around. Axial is up and down along the axis. If axial is free, that means the part is allowed to move up and down along the axis about which the support is presented. And the final being tangential. Now, with radial being radial to the axis, axial being axial to the axis, tangential is one which represents a rotational degree of freedom. Can my component rotate about the axis about which the column support is enacted? So keeping all of these three in mind, let's go ahead and head over to our FEA model where we can start applying these supports. Before we apply these supports, again, like I said just a tiny bit earlier, we need to understand how everything fits together in our CAD model. So let's go ahead and open up our assembly. Now in our assembly, we can see over here that our control arms are connected to the frame and connected to the upright. Now, with everything fully allowed to move, I'm going to suppress my recenter mates over here, excuse the rebuild errors. But we can see that our control arms are actually allowed to move up and down. Now, at any given point when a force is enacted through these control arms, we're going to pretend that the wheel and tire, that the wheel and tire are both in contact with the ground, meaning that our control arm cannot necessarily move up and down as a result of the loads because the wheel and control arm are in contact with the ground. So let's look at our inboard points. Now on our inboard points, we can see that radially, this point is constrained. It is not allowed to move because there is a bolt passing through this center point right here. So radially, like I said earlier, we cannot move around. Now axially, can this move up and down? Well, it's not modeled in this assembly right now, but we're going to have spacers between the spherical bearing and the controller mount. So, like I mentioned earlier, axially, we're going to be constrained. It's not going to be allowed to move. Now, will we be able to move tangentially? That is that rotational degree of freedom. I would say yes, because this represents a spherical bearing. And so being able to rotate tangentially is an inherent characteristic of a spherical bearing. It is always allowed to rotate about the axis along which the bolt is passed. So that covers our constraints for the inboard side. We're going to have our radial as fixed because deformation is not allowed. We're going to have our axial as fixed because deformation is not allowed. And finally, we're going to have our tangential as free because rotation is allowed through the constraints that we have. Now let's look at the outboard. where it connects to the wheel and tire and upright assembly. Over here, we can see that radial is not allowed because we have a bolt passing through here. But this is where the force is enacted. So we want to be able to measure deformation at the outboard node. This is the part that's a bit mobile. We can see that if there is radial deformation, that deals with changes in our kingpin axis. So we're going to leave our radial as free. Axial, we can say, is not allowed. The control arm itself is not allowed to move up and down because of constraints in the clevis over here where it bolts. We're going to have spacers over there. And tangential, like we said earlier, is free because that point is allowed to rotate. So for the outboard, we're going to have radial as free, we're going to have axial as fixed, and tangential as free. Once again, going over the support conditions for our inboard and outboard points. For the inboard over here, we're going to have radial as fixed, axial as fixed, and tangential as free. But if we move over here to the outboard, we're going to have radial as free, we're going to have tangential as free, and we're going to have axial as fixed. So let's move on over to our FEA model and insert each of these conditions into ANSYS. Now, to apply each of these conditions between the inboard and outboard nodes to our ANSYS model, we're going to be using the static structural node over here. At the top in this menu of selections, we're going to click the drop-down menu on supports and hit cylindrical support. The first round of supports we're going to apply are inboard supports. These should be applied at the inner diameter face of the bearing. Again, like we said earlier, this represents the bolt hole that will be going through the spherical bearing. This is, again, a dummy bearing, so it's not meant to accurately represent a spherical bearing, but represent something of similar shape and size made of a similar material. So again, we're going to apply this geometry to our cylindrical support. Like we said earlier, we're going to leave radial as fixed, we're going to leave axial as fixed, but we're going to change our tangential constraint to free. And while we're here, we're going to rename this to inboard supports. Now it's time to apply our outboard supports. So again, drop-down menu on supports, cylindrical support. We're going to come into our outboard node and apply it to the inner diameter of our dummy bearing. Like we discussed earlier, we're going to leave radial as free. We're going to leave tangential as free and leave axial as fixed. Once we're done with that, we're going to rename it to outboard supports or outboard support since there's only one node. Now that we're done with that, we're going to select both of these supports and add them into a group named supports, or add them into a folder. Once those have been applied, it's time to now apply our loads. Now, when we analyze control arms, we apply one of 5 control arm loads. That is maximum braking, corner entry, mid-corner, corner exit, and maximum acceleration. These represent one of the 5 phases of taking a turn in a Formula SAE car. That is, braking as you approach the turn, corner entry, which is a combination case of braking and cornering acceleration, max cornering, which is the absolute maximum lateral Gs that you can achieve with your car, corner exit, which is a combination case of cornering Gs and longitudinal acceleration, and then max acceleration, which is the absolute maximum longitudinal acceleration that the car can see. So we have to make sure that we represent one of each of these 5 cases for the control arms. One thing to remember going into this is that each of the nodes of this control arm have spherical bearings. So it is a moderately reasonable assumption to see that each of the arms of the control arm tubing are 2 force members. So now to apply the proper forces along the plane of this control arm, we have to create a coordinate system that lies along the plane of this control arm. So we're now going to start by over here clicking on coordinate system, right-clicking that, hitting insert, and then hitting coordinate system. So We're going to start with defining our origin, which will be the inner diameter of the dummy bearing of the outboard dummy bearing. We're going to hit apply. And when it comes time to define how our coordinate axis sits, we're going to start with our principal axis section over here. And we're going to start with our y-axis. So we're going to go ahead and select y. We're going to let it be defined by geometry. And we're going to select the bottom face of the bearing cup. As you can see, this lets the y component of our coordinate system be exactly perpendicular to our bearing cup. We're now going to let the x component be parallel to the global x component. So again, orientation about the principal axis, we can see the x component is already pre-selected. We'll let it be defined by the global x-axis. So now, again, if we come around to look over here, we can see that the y-axis is perfectly perpendicular to the bearing cup that sits over here. Oh boy, I forgot to restart the lo-fi music. Hold on, let me make sure that this is... all right. Well, hopefully you all can hear the sound by now. All right. So we can see over here that the actual coordinate system is perpendicular to the bearing cup. This means that when we apply a load, we're going to be applying bearing loads, and bearing loads do not enjoy axial components. When we apply a bearing load to the inner surface of this bearing over here, the dummy bearing, when we apply it in terms of x and z components using this custom control arm coordinate system, we can ensure that nothing has an axial component. The number one thing with bearing loads is that you cannot have an axial component because it will absolutely ruin just about any load you're trying to enact on it. It'll crash the solver and it won't give you a solution. So now that we've created this coordinate system, we're going to rename it over here on our left tree to arm coordinate system. And we're going to make sure that I spelled that correctly, which I don't believe I did. Coordinate. Okay, awesome. Got it right that time. So now, just like that, we've created our supports for the inboard and outboard sides, and we've also created our global or arm-specific coordinate system. Now it's time to apply the loads. So what we're going to do is click on our static structural heading right here. And on the drop down for loads, click bearing load. Select the inside diameter of that bearing, hit apply. And we're going to do that 4 more times. So I'll see you guys once I do that. Feel free to pause this video and go ahead and complete those steps. All right, welcome back. Hopefully you paused the video and worked through each of these steps. We're now going to resume where we left off after inserting each of the 5 nodes. So we've got bearing loads 1 through 5. We're now going to go through and name them individually. The first being max braking, second being max cornering, corner entry, third being max cornering, fourth being corner exit, and fifth being max acceleration. Again, I want all of you to think about each of these stages of cornering a Formula SAE car in the process that they happen. As you approach a corner, you're going to hit max braking first. You're going to hit that brake pedal, meaning your first load case is going to be max braking. After you hit that brake pedal, you're going to slowly start to turn in the wheel, meaning your second case is corner entry. After you start your corner entry, you're going to slowly let off that brake pedal and reach a steady state cornering situation, meaning your third case is max corner. After you're done cornering, you're going to slowly start to roll onto that throttle and develop longitudinal acceleration, meaning your fourth case is now corner exit. After you're done exiting that corner, you're going to straighten up that steering wheel, get fully on the throttle, and try to accelerate as hard as your Formula car possibly can, meaning your fifth load case is now maximum acceleration. We do each of these based on the G-forces that we expect, depending on our aero package and other vehicle dynamics characteristics at the time for each of these packages. But solve for each of the loads at each of these situations, and rename each of your 5 load cases accordingly. As you can see over here on the left side of my tree, we can see 5 bearing loads that have been applied to the exact same contact on the inside of the dummy bearing And I'm going to go ahead and now rename each of those to represent each of the 5 load cases. All right, and now that we've got each of our 5 load cases defined in terms of their geometry selection, it's time to define each of their components. So I'm going to go ahead and share my screen once again to the ANSYS selection portion. And we're going to start with our max braking component. Now, do keep in mind that each of the loads for these components will be found from your control arm geometry designer. They're going to solve for the load cases that each of the control arm geometries is going to see and tell you exactly which X and Z components to expect. X being pointing towards the left of the car and Z being pointing towards the back of the car. So we're going to start with our max brake. We've defined the bearing load to be at the inner diameter of that dummy bearing, but it is currently defined by a vector as seen in the bottom left of my screen over here. We're going to change that to be components and change our coordinate system to be arm coordinate system. Now over here, we're going to enter placeholder values for our X and Z components. Again, do make sure that you do not enter a Y component because that will exhibit an axial load along the bearing load, and ANSYS really does not like that. So make sure that you're only exhibiting radial loads to the bearing load. So for our case right here, it's going to be X and Z components. Right now, as placeholders, I filled in 10 newtons for the X component and 10 newtons for the Z component. Go ahead and do this for all the rest of the load cases. The actual control arm component designer will come in and fill in the X and Z component values later on, or they will tell you exactly what they need to be. They should be in a compiled load case Excel sheet, but if not, please talk to your designer and see what loads you're expecting at the outboard node of your control arm for each of these individual simulation situations. Now I'm going to go ahead and fill these in for the rest of them for 10 newtons as a placeholder value, and as soon as I'm done with that, I'll be right back. All right, everyone, welcome back. I just finished completing the load case definition for our outboard node of the control arm. So we're going to go ahead and share my screen. As you can see on my left side screen, or my left side tree over here, we see max brake through max accel, all fully defined. Each of them holding our placeholder values of 10 newtons in the X direction and 10 newtons in the Z direction. Again, these are placeholder values. Please contact your designer to make sure what exact values you're supposed to be using. For now, having these placeholder values allows us to run the model and see whether or not we're having actual failures. Now we've completed our support definitions and we've also completed our load definitions. It's time for us to mesh this part and ensure that we get accurate results. So we're going to move all of the loading forces into a group called loads and minimize that. Again, do ensure that your file structure and your file format is completely accurate and very, very much readable. In the industry, there's going to be a lot of times where you face people that don't really know what they're talking about reading your files. You want to make sure that no matter how less educated or contextually uninformed this person reading your file is, they want to be able to understand what is located where in your file. So now by labeling everything as supports and loads, we've pretty much toddler proofed our file. People are going to know what lives where for each of these. And now again, as we've defined the supports and the loads for each of these, it's time to define the mesh. We're going to navigate to our left tree over here where my cursor is. We're going to right click mesh, hit insert, and the first option we're going to click is method. So we're going to select the control arm body, the dummy bearings on each of the nodes, and along with those, also the snap rings on each of the nodes. Again, be sure to select every single thing that's part of this assembly because it is essential that we cover all of our bases. Once we hit OK on the geometry, the first thing we're going to do is change our method selection from automatic to tetrahedrons. From there, we're going to change our element order to quadratic. Now that we have quadratic tetrahedrons representing each of our components, we can ensure a slightly higher accuracy of results as it more reasonably estimates what sort of deformations and stresses we can see from this component. Since we've done that, we're going to right click again on mesh, hit insert, and then our next option is sizing. We're going to have 3 individual elements of sizing in our tree. The first being for the control arm body. I started this one at a 2mm mesh, but please, if your laptop is capable of it, run a finer mesh because a finer mesh is going to give you more accurate results. From there, we're going to rename this to be the tube mesh. Now we're going to right click on mesh once again, hit insert, sizing. We're now going to size each of our dummy bearings. These are important, but they're not quite as important as our control arm tubing. So we're going to make them a mesh size of 2mm. Rename them again to bearing mesh. Now it's time to insert our last mesh item, and that is another sizing element, and we're going to choose the snap rings. Now the snap rings on these control arms are quite small. After we apply that geometry, we're going to change the element size to 1mm. We want this mesh to be nice and fine. The finer a mesh is, usually the better the resolution of the answer is. Once that is completed, we're going to rename it to snap ring mesh. Awesome. And now that we've completed our support conditions, we've completed our load conditions, and we've also completed every single one of the contact conditions for our part, I believe it's ready to run. Before we do that, we're going to go into solution over here and add elements of directional deformation, total deformation, equivalent strain, and equivalent stress. Once we have all of these solution types loaded in, it's time to actually solve for our answer. Before we solve, the number one thing to do is to look for how many cores your PC might have. I've opened up Task Manager over here, and we're going to look at performance. In the Performance CPU tab, my Task Manager tells me that I have 6 cores. We want to follow generally the N-1 rule, where when we're running ANSYS or when we're running FEA, we want to use or utilize N-1 cores from what we have available. I have 6 cores available on my CPU. Therefore, using the N-1 rule, 6 minus 1 is 5, I'm going to use 5 cores for my ANSYS FEA. So clicking on the Home tab here in the top left corner, I'm going to navigate over to cores, and I'm going to make sure that I have 5 selected, no more, no less. This way my solution will run as fast as possible. As soon as I've done that, I'm going to hit the Solve button while having solution information selected. Now, once I hit solve, it's going to start solving the mathematical model that it has set up, and from there we're going to start seeing actual solution information outputs. Once I start seeing those a bit more significantly, I'll resume this video, but until then, run your simulation, pause this video, and we'll see where you end up. All right, so coming back real quick to our model from earlier, I did have to upsize the mesh resolution from 2mm, or the mesh size from 2mm to 1mm for our control arm tubing, and that's because the mesh failed to actually mesh. This can happen pretty often if you choose too rough of a mesh density for the component that you're trying to analyze. It can fail to actually evaluate that mesh. Or if you create too fine or too weird of a mesh geometry, it can fail to create that mesh. So make sure you play around with these numbers to actually ensure that your model is able to solve. Now, after changing the mesh geometry or the mesh size from 2mm to 1mm, I am now able to generate that mesh and the model can actually solve. So please feel free to pause this video to actually solve your model, and I'll see you once that finishes. So, funny story. Welcome back to the video. When we last left off, I was filming that pretty late at night / early in the morning. I kind of fell asleep. Welcome back. It's the next morning, and like where I left off, we finished completing our model. All we have to do now is run it. So that's what I'm doing. I'm running the ANSYS file and it should be able to run. Again, this does take a while, but we've gone over all of the boundary conditions. We've gone over how to set the file up, and that's really all we need to know. Thank you for your help. I hope you learned something, and I'll see you in the analysis portion of this video, which I'll be posting soon. Have a good one.